Sorry, video cut out right there. We're just going to pick it up right here with the vase that is at rest and remains at rest. So we saw that if you push it with 5 to remain at rest, you got friction cancels with -5. Now if I push a 10, friction is going to, if it remains at rest, friction always is pushing back with an equal amount. -10, right? Because if it remains at rest, the net force must once again equal 0, right? Now there is a limit to friction. Alright, so draw your vase again, and what do you think? We're going to push it positive 15. Eventually that vase is not going to remain at rest if you push hard enough. So if we push with 15, did we overcome friction, right? Well, say our limit of friction in this case is 10 newtons, so friction can only apply up to 10 newtons of force, right? So if I push with 11, will it budge? Yes, because there will be a net force will be left over. 11 minus 10 is 1. The net force would be 1, right? If I push with 12, the net force would be 2. If I push with 13, the net force would be 3. And no longer would it remain at rest. It would accelerate. So, this should be in our budges from rest category right here. So if I push with anything 15 newtons, right, then my friction remains 10, -10, right, and I would have a net force. In this case that I drew, the net force would be 15 minus 10, 5 newtons. So in the case where you have a net force, where there's some left over, objects at rest do not remain at rest. And anything sitting on the ground, if you push harder with more force and with friction can push back, then there's a leftover, there's a net, and the object will not remain at rest, it will accelerate, right? So budges from rest, what causes that? It's what we call an unbalanced force. When there's an unbalanced force on an object, two forces are unbalanced, then there's a net, there's a leftover, and that object does not remain at rest. It budges from rest. So, but in these two cases, case 1 and 2, what you have is you have a balanced force. And a balanced force means, there it is right there, means the net force equals 0. Because, like the case where we push with 5 and -5, 10 friction pushed back with -10. The forces canceled out and they balanced out. And our official vocab term for that is a balanced force when they add up to 0. In the case of a balanced force, an object at rest does remain at rest. Alright? Alright, so let's look at motion as our next example. On the right side of the page here. In motion, does not remain in motion. So I wanted to look at an example similar to sliding along the floor like we looked at in class. Let's just take a sled, draw a little trapezoid with some little skis on the bottom, and you got a sled. So, and it does not remain in motion, so it decelerates. So normally a sled going along the snow doesn't immediately come to a stop, but it's slowing down, decelerates, right? If nobody's pulling it. So here we're just going to write no pull, right? There's no pull on the sled, no rope pulling it. But friction, if it's moving to the right, friction between the snow and the metal bottom is always acting. let's just give it a negative 10 newtons or something like that, you know. But if there's no pull on the sled, then what's the net force on the sled? Well, usually you would add up friction and FP to get the net, but here there's no FP. Nobody's pulling, so the net is just due to friction, and the net would be a negative net, and that's why it slows down. It experiences this negative acceleration, right? Because there's a negative net force. And other examples of that include things like a hockey puck sliding along the ice eventually stops. You think of your own. Add one here. I always think of a baseball player sliding into second base. Negative net force slows down, due to friction. Or another really good one you might remember when you were little is the slip and slide. But I want you to add one of your own, all right? So how to keep an object in motion? Well, how to take this sled and just to make it keep moving instead of slowing down, right? So 2 ways to do it. You can make one, a slicker surface. So if you take the sled, why does a slicker surface keep it in motion? Well, we know, based on Newton's first law, in the absence of a net force is when an object in motion stays in motion. Here, there was a negative net force, so it didn't stay in motion. But a slicker surface would take this force of friction and it would completely eliminate it. So if you had like an oil slick surface and you just got rid of the friction force, theoretically it's possible, but it's very tough to do it. Then the net force would be equal to 0 and an object would stay in motion. But the second way to do it, much more practical, is to use this concept of balanced forces. Take your sled, right, and there's always going to be that friction force slowing it down if it's sliding there, negative 10, right? There's always going to be that. Let's see if we can get that a little nicer. Force of friction equals negative 10 newtons. There we go. But what you could do is you could balance friction by pushing it or pulling it with a rope. Apply an FP of how much to keep it moving at a constant speed in a straight line. Positive 10, right? It's because 10, positive 10, negative 10 add up to a net force again of 0. So objects at rest remain at rest when net force is 0, but objects in motion also remain in motion. All right. Now, what if you took that sled and you didn't apply an equal force to friction, but you applied, I'm going to draw a longer arrow to say, what if you applied 12 newtons of force and friction, it's only been given you negative 10. What would happen to that sled? Well, the net force wouldn't be 0, so it wouldn't stay at a constant speed. The net force would be positive 2. When you had a negative net force, the sled slowed down. It experienced a negative acceleration. But if you push harder than the 10, it's not that it just stays in motion. If the force is balanced, then it stays in motion. But if you to speed it up, you would need a positive leftover or net force, right? So it would experience this positive acceleration when you push harder than friction, and that would be, once again, an unbalanced force. where it doesn't remain what it's doing. The balance falls in the positive direction this time, so it speeds up.